This is a video on valency, a very important concept in chemistry because from the ideas relating to valency, you can get into things like chemical bonding, so how atoms of particular elements combine and how chemical reactions work. So it's a very powerful concept. The word itself is actually Latin, comes from Latin valentia, meaning strength. You don't need to know this for any exam or assessment. It's just nice to know where words come from, okay, because it gives you a bit of context. So in that regard, valency is basically, the best way I can define it is an atom's combining power. So in other words, it's basically the ability of an atom to combine, the relative strength of an atom to combine with some other atom, okay, for some other particular element. Another way to say it is it's basically the number of atoms of a specific element that's combined with one atom of another element, okay, to form a molecule. Because by definition, a molecule is two or more atoms combined. So we'll see how this works. Another way to think of valency is basically the friendliness of an atom. Okay, how willing it is to bond with other atoms. Okay, it determines how an atom can bond with other atoms to form molecules. That's how I can think of it. That's how I often think of it, actually. So to understand valency, let's get into valence electrons. So the outermost, so a valence electron by definition is simply an atom's outer electron. Okay, there could be more than one valence electron. So for example, let's do lithium. Lithium, so I'll draw the nucleus like that with the words, with the letters Li for lithium. Lithium has 2 electrons in the inner shell, because only 2 electrons can fit in the first shell, and a 3rd electron on the second shell. This 3rd electron is the valence electron for lithium. It's the outermost electron. Okay, let's do sodium. So sodium has an atomic number of 11, so it's got 11 electrons. So 2 electrons in the first shell, that's the rule, and 8 electrons, so 2, 4, 6, 8 electrons in the second shell. So the first shell, if you recall, can only fit 2 electrons, a maximum of 2 electrons, 2 electrons max. The second shell can only fit 8 electrons. We don't tend to go more than the second shell, okay, typically in exams, for example, because it takes sometimes forever to draw atoms with more than it's just time consuming drawing atoms with more than 10 electrons. But anyway, so 8 in the second shell, and it's got 1 valence electron, 1 outer shell electron. And what we can see here is that lithium and sodium, because they're in the same group, they've got the same number of valence electrons. So that's the rule with valence electrons. Okay, so elements in the same group, so in this case the alkali metals, have the same number of valence electrons. It's a very simple principle. That's just the way nature is. That's how atoms have formed in the universe. That's how it is. Okay, so that's the idea of valence electrons. Now the periodic table actually can help you as a guide in terms of knowing how many valence electrons there are in a particular element by looking at the groups. So because I don't have the periodic table here, I'm just going to write down the names of the groups. Group 1, Group 2, Groups 3 to 12. So these are the transition metals. 13, 14, 15, 16, 17, 18. Group 1 has 1 valence, so each element has 1 valence electron. Group 2 has 2 valence electrons. Groups 3 to 12, I'm going to write depends. In an exam, they'll tell you, okay? Because transition metals vary in terms of their properties, etc. So for example, iron could have 1 valence electron, could have 2, could have 3, could have 4. Okay, same with copper as well. So 3 to 12, don't really worry about this one too much, because I'll often tell you in an exam. Group 13, they've got 3 valence electrons. Group 14, 4 valence electrons. You can probably see the pattern here. Group 15, 5 valence electrons. Group 16, 6 valence electrons. Group 17, 7 valence electrons, outer electrons, and group 18, 8 valence electrons. Okay, that's the pattern. It's quite simple. For groups 1 and 2, it's just 1 and 2 valence electrons. 3 to 12 depends. 13 onwards, just simply take off the first digit. Just does a nice trick. Take off these digits here. Okay, and very simply, they're the valencies respectively. So that's how many outer shell electrons all of these groups have. Okay, each element in these groups have. Now for valence, so metals, the periodic table is made of metals and non-metals. And metals, typically, they like to give away electrons. Whereas non-metals, this is the fact of life, this is the fact of nature. It's how nature is built. Non-metals typically gain electrons. They like to gain electrons. And I'll explain why. Makes perfect sense from an intuition, train of thought, I should say. Okay, so metals. So let's take lithium, for example. As I mentioned before, lithium has 3 electrons. It's got 1 valence electron. Now atoms, another important note, atoms, they've got one goal, and that goal is to become stable. To become stable, you have to have a full outer shell. Full outer shell and become stable. What do I mean by stable? I mean that stable in the sense that it won't react with any other atom or element. Okay, it'll stay as it is. That's what an atom wants to do. So lithium has 1 outer shell electron, 1 valence electron. It's much easier for it to get rid of that electron than to gain 7 others and have a full outer shell, right? Because lithium's second shell, the second shell can only fit 8 electrons, right? And it's got 1 electron in the outer shell. It prefers to get rid of it. Okay, it's less energy, less effort. So it gets rid of it, and now it's got an overall charge of +1. Why is it +1? Because atomic number of 3, so it's got 3 protons, and now it's got 2 electrons because it's given away 1 electron. So 3 minus 2 is 1, so it's +1. So by convention, that's how we write lithium. Li, the symbol for lithium on the periodic table, and then +1 at the top. You can leave the 1 out if you want, because plus and +1 mean the same thing, but anyway, it's nice to write it there. +1 means the lithium loses an electron and has now a net charge of +1, an overall charge of +1. Same thing with sodium, Na. It's got 2, 4, 6, 8. It's got 11 electrons. Okay, it's in the same group as lithium, group 1, so it would rather give away that electron, okay, to have a full outer shell. So when it gives away that outer electron, it's now going to look like this. It'll now have 10 electrons. Okay, so the first shell's got 2, second shell's got 8. It's stable, it's happy. Sodium is written like this, Na +1, because it's given away 1 electron and now has an overall charge of +1. You can think of it this way as well. Instead of looking at it in terms of this picture, if you're more mathematical, think of it like this, or you can think of it like this if you're more conceptual, more of a visual person. It gives away 1 electron and now has a net charge of positive overall charge of plus, right? Group 2, for example, calcium. If I was to draw calcium, look like this. Okay, so that's the idea previously here, that group 1 has a valency of 1, right? Group 1 elements have a valency of 1. Calcium looks like this. It's got 2 valence electrons. Actually, I'm not going to draw all of it. I'm just going to draw the outer electrons because it's too many electrons to draw. So let's pretend I'm only drawing the, I've drawn everything else and I'm now drawing the outer shell. It's got 2 valence electrons. Rather than gaining 6 electrons, it would rather get rid of these 2. Okay, so it will now have stable shell, a stable configuration. It'll have stable inner shells. So the calcium is now stable because it gets rid of 2 electrons. So we write it this way, Ca plus 2. It's given away 2 electrons and now has a overall positive charge, okay? You can also think of it this way. Let's suppose, so the sodium that we're familiar with all around us in our salts, in everything, in our bodies as well, in our bloodstream, sodium is neutral. Neutral means there's a balance, just like all atoms typically that we see, that we encounter every day. There's a balance of positive charges and negative charges. When you remove negative charges, you're now going to have an imbalance, and it's now going to have an overall charge of plus, right? So the calcium now has an overall charge of plus, okay, and 2 because it's given away 2 electrons. Okay, magnesium as well is in the same group as calcium. It's got 2 outer electrons, gives away those 2 electrons. It now has an overall charge of plus, okay, and it's given away 2 electrons. It's got a valency of 2. So they're the metals. Let's get into the non-metals. Let's look at chlorine. Chlorine's a good one. So I'll try and draw chlorine. Chlorine's got an atomic number of 17. So 2 in the first shell, 8 in the second shell, 11, 12, 13, 14, 15, 16, 17. It's got 17 electrons. It's got 7 electrons in the outer shell. It would rather gain another electron to achieve stability, to become stable. Yeah? So when it gains an electron, so chlorine before, right, has 17 electrons, 17 minus charges, and 17 protons, 17 plus charges. So it's neutral, it's balanced. When it gains another electron, it's now got 18 minus charges. So the chlorine is written like this, the chlorine, valency for chlorine, Cl minus 1. Minus 1 because it now has a net charge of minus, and 18 minus 17 is 1, right? So it's got 1 extra electron added to it. That's why the 1's there. Minus charge overall, and 1 electron it gains. Similarly with fluorine in the same group, and bromine and iodine, etc., they all gain an extra electron to now have a net negative charge, okay? If you give negative charges to a neutral atom, it will now become negative overall. That's the logic. Let's do oxygen. So oxygen is in group 16. It's got an atomic number of 8. So 2, 3, 4, 5, 6, 7, 8. It's got 6 electrons in its outer shell. It would much prefer to gain 2 more electrons. So when it gains 2 electrons, it's now going to have a net charge of minus, okay? So write it as O with a minus 2. Minus net charge of minus, negative, and it's gained 2 electrons. Let's do nitrogen, which is in group 15. So oxygen is in group 16. It's got 6 outer electrons, but would prefer to gain 2 more to have a full outer shell. So it's now minus 2. That's the convention. That's how we write oxygen when it gains 2 electrons to minus 2. Okay, instead of just O as seen on the periodic table. So nitrogen has 7 electrons. So 1, 2, 3, 4, 5, 6, 7. And to achieve a full outer shell, it's got 1, 2, 3 gaps for 3 electrons. So it wants to gain 3 electrons to have a full outer shell. So it's a non-metal. Being a non-metal, it wants to have a minus charge overall. So it's N minus 3. Now the noble gases, these are particularly special. They've got a valency. For example, helium has a valency of 0. The noble gases are unreactive, also known as inert. They don't want to react. They've got a full outer shell. Helium has 2 electrons, only 2 electrons, so it's satisfied. Neon as well, it's got an atomic number of 10. So it looks like this: 1, 2, 3, 4, 5, 6, 7, 8. Also full outer shell. So normal gases have a valency of 0. So I'll recap. Metals tend to lose electrons to become positive overall. Okay, these are called cations. Okay, charged atoms with a positive charge, net positive charge, are called cations. Now think of cool, calm, and collected. Here's a nice memory device I like to use in my classes. Okay, when you're cool, calm, and collected, you're usually positive with a positive attitude. So C for cool, calm, and collected, cations. And non-metals like to form anions. They like to have an overall negative charge. Apologies, I should say before. I made a mistake in saying that metals tend to have a negative charge. They tend to have a positive charge overall. They want to have a positive charge. And non-metals want to have a negative charge overall to achieve stability. Okay, anions. And think of N as in negative, yeah? Negative charge. So metals like to lose electrons to become positive overall, and non-metals like to gain electrons, to become negative overall. That's the idea. That's valency. It's an atom's willingness to combine with other atoms to achieve stability.